Physarum polycephalum, one of nature's networks. I am here today to talk about a wonderful organism affectionately nicknamed the blob by French scientist Audrey de Sauter. In this project, I chose to investigate whether Physarum polycephalum could recreate common networking topologies. The potential applications could prove to be useful for supplementing the design of computer networks, a tool to assist in their development, reducing the volume of resources required to design them. What is Physarum polycephalum? Slime mold, the blob. Like other molds, such as Foligo septica, affectionately known as dog vomit slime mold as per its bio-like characteristics, or Enteridium lycoperdon, commonly known as the false puffball, and many more, it plays an important ecological role. It aids in the decay of organic matter, breaking it down and returning the nutrients back into the food web. The blob has a growth behaviour that closely resembles the formation of modern man-made networks, and it is speculated by some that it inspired networks in use today. Although we specify it as a mould, it isn't actually a mould at all. It is a member of the protist kingdom, which categorises organisms that could fit into either the fungus, plant or Monera kingdoms. It is cognitive, yet without a brain, without a central nervous system. It can solve maze-like puzzles and even learns about other substances. Its behaviour drew my attention to networking topologies, which play an important role in the development of networks, determining scalability for these networks' growth, resilience with redundancy and alternative pathways, as well as optimizing the required resources. The choice of topology also governs the efficiency of a network's communication and the capacity to manage that network. Researchers are often inspired by nature in their endeavours. The burrs of many plant species, pods with hook-like characteristics, inspired George de Mestral's invention of Velcro in 1941 while walking one afternoon with his dog, as they stuck to his clothes and his dog's fur. Hydrophobic properties were inspired by the lotus effect of the lotus flower, the water rolling away from the leaf as though repelled, and of course, most famously, Leonardo da Vinci's flying machines inspired by the sparrow and then the hawk. So why exactly are there advantages to the inspiration of nature alongside science? Biological organisms have evolved over eons to adapt to their environments, evolving in spectacular ways to survive and tackle the various risks in these environments. Physarum polycephalum has evolved to form efficient networks between food resources, and because it is living, it holds survival in its highest regard, much like our networks rely heavily on redundancy, tolerance, and efficiency to remain operational. Although limited in my resources to design and complete this experiment, I had no lab to work in, neither did I have access to many of the tools and equipment one would associate with a lab setting. With this concern, I began my experiment with a short feasibility study to make sure that the blob could survive in its intended experimental environment. This was not a taxing endeavour. I placed a specimen of polycephalum onto 2 agar plates with some oats and placed them on a baking tray under a set of drawers, paying no heed to anything that could increase the risk of contamination or the perishing of my new pets. This was intentional, as I only needed to know if it could grow successfully in the least effective environment, because the average networker, much like myself, does not have a scientific environment expected for such an experiment, and it would not be all that useful if we needed such a massive investment just for a tool. This study was somewhat successful. With this, I then went on to design the main experiment. I purchased a handful of tools and equipment, most importantly a sealed tub as a sterile environment, after cleansing it with 99% IPA alcohol. A set of rubber gloves and some lab-grade tweezers for handling of the polycephalum was also required. I then allocated food resources to 6 agar plates. 2 sets of plates were required, one set as a control in the less sterile environment, and one set inside the tub. That's what you see there. The food sources were laid out into common networking topologies: star, point-to-point, and ring. Then I left them to do their thing. After a week of growth, and before the polycephalum started to migrate from its agar plates, I then applied a hit-or-miss system to measure how well my blobby little pets had recreated these topologies. I'd like to show you the data first, then the visual results. What you see here are measurable results of the hit and miss system. It is, as you can see, a mixed bag, and shows more than anything, at least, that with an increase in networking complexity, accuracy falls. This is due to the volume of biological matter on the plates, providing opportunities for contaminants to flourish rather than a failure of the blobs. They also suggest that a more controlled environment would provide better results. To my dismay, these results suggested that polycephalum is not an applicable tool for your average networker, not without a larger investment into a more appropriate environment and the equipment to go with it. However, the visual results tell a different story. Now, would you look at that? This is the point-to-point agar plate from the sterile environment of the alpha set, which succeeded in its role. It is unlikely that one would need to deploy such a tool for a simple network like this. However, it was important to include a simple design to ascertain any limitations as complexity increased. The next plate is its beta counterpart. Because of the introduction of airborne bacterium from its environment, connections formed everywhere. A point of disruption also formed, which I morbidly dubbed a tumor node. Perhaps if the same thing had happened on the other side, it could have been speculated that polycephalum was attempting to create something akin to a repeater or hub in a network with 2 connections running between each node. Alas, this was more likely to be a small formation of fungus. The next network you are about to observe is much more interesting. If it was not for the tumor nodes that formed at points G and H, this plate would have been a fantastic success. It was extremely close to forming the expected ring topology, with only tumor node G disrupting its final pathway. Furthermore, it developed connections across the center of the plate in a logical formation one could certainly use as suggestive links in one's own network design. A designer may consider the ring at the center a good place for a multi-layer switch, with the outer intermediary devices being routers. Its counterpart beta plate, from the perspective of an applicable tool, was not a strong contender. It grew in a wild manner, and although there are connections, it was only my own generosity that allowed these connections to be considered a success. They simply aren't strong enough in retrospect. The final plates are the star formations. This is the alpha star, the sterile environment star. It was somewhat successful, however. Polycephalum retained its plasmodium state in the southern section of the plate, making it difficult to isolate any realistic connections. They are likely there, but not easily observed. I predicted that the star formation would be the most successful, given the central node allowing polycephalum to spread equally. I also predicted that it would form a ring around the outer edge, which it tried to do, but they are not strong connections, so I considered them moot, or at least open for debate. And finally, the unexpected occurred with the beta plate from the control environment. It had 2 tumor nodes, disrupting connections to the expected nodes. However, it performed its network as predicted and even formed strong connections between the nodes as a ring and a star. This is what I wanted to see. Yes, there is an amount of overgrowth, however, the standout connections are clearly visible, and my pet Blobby here performed admirably, forming extra links where one might decide to implement into our own networks for fault tolerance and redundancy. Before finalising this presentation, I must mention some critical errors, or more accurately, learning experiences within this experimentation. The experiment I have included in this presentation is one of 3 that I conducted. The first 2 experiments were botched by a single error, my assumption that all agar plates were made equal. This was not the case. I couldn't even tell you now what type of agar plates I used with the first experiments. However, what I can tell you is that Polycephalum was growing in a strange breadcrumb-like fashion, indicating that perhaps it was focusing on consuming the agar and not attempting to seek out the food resources provided. With little time left, I conducted more research and discovered this error. More research suggested that malt extract agar plates would be the most successful, forcing Polycephalum to work for its food. My second critical error was a failure to abide by anything remotely akin to the scientific method. It was brought up in university, and my heart sank as I realised I had not even considered this. I went for a best effort approach to fix this on the final experiment, and it came together quite nicely, with controls in place, independent and dependent variables, as well as variables outside of my control: temperature, light levels, moisture levels. I do not regret these mistakes. They were learning experiences. I am not a scientist, neither am I performing on a science degree, highlighting yet another limitation of these experiments. The results of this project have been fascinating, and I will hopefully inspire more research into the efficacy of Polycephalum for creating computer networks. I thank you for your attention, and hope this has fascinated you as much as it has I. I now open the floor to questions and discussion. Thank you.